We are finding more and more exoplanets, more and more locations for liquid water, and the possibility for life as we know it. But where are the alien civilizations? Where are the technologically advanced creatures? Why can't we find signs of other sentient beings? Where are their signals out there amongst the stars? Perhaps the answer to that age-old question, are we alone in the galaxy, is a yes. American astronomer and astrophysicist Frank Drake established the search for extraterrestrial intelligence, or SETI, back in 1960. Listening to the stars and the noisy galaxy, trying to find signals that are deliberate, messages from other planets where life has evolved an intelligence, a technological civilization like our own, able to comprehend the vastness of space. Like us, looking for the answer to that age-old question, are we alone? There are 3,700 known exoplanets so far. NASA's TESS is going to find lots more. The European Cheops mission will specifically study the known exoplanets and look for more around our brighter stellar neighbors. Multiple planetary systems and terrestrial, Earth-like planets are coming up trumps, and we've only been looking for 15 years. We have been looking and listening for nearly 60 years now with zero results. No radio signals, no laser or other light flashes in our direction, no attempts at communication that we can detect. So where are all the aliens? Well, it's a complicated question. Stars that can harbor Earth-like planets, viable exoplanets that can sustain liquid water. As for life, how long does it take to generate life? Then, how long to evolve into intelligent life? Will that intelligent life become technological? How long will an advanced civilization survive? Tough questions when you only have Earth as your example. Then there is the time factor. The universe is 13.8 billion years old. Our star, the Sun, is 4.6 billion years old, and probably a third or fourth generation star. Earth is 4.543 billion years old. Our moon is just the right size to stabilize Earth's rotation and provide ocean tides and sea currents. Life on Earth is at least 3.5 billion years old. Several major climatic and asteroid interventions steered the evolutionary cart leading to us, Homo sapiens, 200,000 years.
I think that's an interesting thing. This one piece will make 52 layers.
Watch on mobile devices or the big screen, all for free. No subscription required.
Our civilization began around 6,000 years. The Industrial Age is just over 200 years. The ability to send signals into space, maybe 100 years. Powerful radio signals, television signals, radar and laser light, say 50 years. Being generous, our signals have traveled out in a sphere with a radius of 100 light years. That's about 1,000th the width of the Milky Way, which is 105,700 light years across. The nearest galaxy is Andromeda at 220,000 light years away. How long will we continue to broadcast? In other words, how long will our technological society last? Some think not so very long. We have to be realists. There will not be too many terrestrial-like planets with liquid water and an atmosphere to support life, nurture that life to evolve over billions of years into a sentient species that may just develop technology and an understanding of the cosmos to want to listen out and respond to a signal from space. There is most likely life out there, but it's not talking to us yet. Let's crunch some numbers. We'll take the arbitrary figure of 100 light years, where a sufficiently advanced society could detect our radio signals. They then work out where the signal came from and dispatch a response. This could take a few years to achieve. Then that signal will take up to 100 years to get back to us. 100 light years in kilometers roughly equals 9 plus 14 zeros after it. What stars are within that reach? We're only looking at main sequence stars, ones that are stable and long-lived, moving through various stages in their lifetime of billions of years. So we have 3,868 stars to choose from, plus a few more very dim ones we haven't found yet. Exoplanet hunters have been targeting the dimmer, smaller stars called red dwarfs or N-type stars because it is much easier to detect planets around them. There are 2,026 stars of that class in our region. They have also been looking at the slightly larger orange K-type main sequence stars. Because of their spectral and luminosity qualities, astronomers favor them for having habitable Goldilocks regions. There are 947 and counting, though there are only 155 within 50 light years. Then there's the G-type stars. Our Sun is a G-type, so they are highly regarded for habitable zones. There are 512 of them. F-types are slightly larger than our Sun, 303 are nearby, and several have known planets. A type which are young stars, a mere 100 million years old, and again have been found to harbour Jupiter-like gas planets, 76. B-type are giant blue stars and rare, only 4 in our region. And supergiant O-types are hot and hostile and nowhere near us. So, how many exoplanets? 3,700 confirmed exoplanets so far. Five Mercury-sized rocky worlds, 72 Mars-sized, 701 Earth-sized terrestrials. (982 called super-Earths), 799 Neptune-type gaseous worlds, and 1,217 Jupiter-sized gas planets. So that gives a current total of 1,683 Earth-like rocky planets. How many of these rocky worlds could harbour liquid water on their surface? Well, there is the habitable or Goldilocks zone around these stars, where the planets receive the right amount of solar flux, where water is liquid. Too close and the water would boil away. Too far and it will freeze, making life more difficult to evolve. So, scientists have estimated there are 17 definitely within this zone. But 3 are outside our distance limit of 100 light years, so that leaves 14. Plus another 13 terrestrials that could seed life, but be very harsh and unforgiving to it. That makes 27 candidates capable of harboring life as we know it.
Life could be incredibly common, because there are lots of planets out there, or it could be an incredibly rare event that only happens, on 1 in a billion planets in a galaxy. We really just don't know. So whenever I get asked that question, my answer is, I don't have an opinion yet. I'll need some more evidence.
TRAPPIST-1, an M-type dwarf star at 39.6 light-years distance, contains a solar system of 7 terrestrial planets and is a major contender for harboring liquid water. They're all Earth-sized candidates. Other multi-planet systems in our region include HR 8832, 55 Cancri, and 61 Virginis. The names just roll off the tongue, each with at least 3 planets orbiting it.
Well, looking at exoplanets, these planets around other stars, is a bit like detective work. They're so small next to a bright star that it's hard to tease out information unless you do it incrementally. So what we can tell right now is that these planets are, in fact, similar to Earth in size, and we can tell that some of them may be similar to Earth in its composition. Doing kind of crude studies of the density of these planets. We're also using the Hubble Space Telescope right now to do follow-up observations of the atmospheres of some of these planets to see the composition of the atmosphere and wondering and trying to find out if maybe there might be water in the atmospheres to see if they are similar to our own Earth's atmospheres.
With names like TRAPPIST, Tau Cetus, Gliese 876, HD 219134, and Wolf 1060, these exoworlds sound ponderous and uninteresting. But one day they may be given more appealing names, because these are worlds with great potential. Elements such as hydrogen, helium, carbon, and oxygen abound throughout the universe, so we might assume that they are available to such planets, and therefore water would be plentiful. Even worlds completely covered in water are feasible. These basic elements also make up the active ingredients for life. Tholins and amino acids are commonplace, so microbial life could emerge on all these target planets quite readily.
Now, we strongly suspect, based on an example of one, our Earth, that the laws of biology work the same everywhere too. And by that I mean the laws that Charles Darwin discovered for us. We think that based on these laws, that evolution can drive life to greater complexity and ultimately to intelligence. It's the smart thing to do.
As with Earth, it could take billions of years for evolution to create ever greater complexity and eventually intelligence. On Earth, most highly intelligent creatures are of the mammalian family, but the octopus developed its intelligence through an entirely separate route. This would indicate that intelligence has many chances of evolving on these worlds. So, why are there no similar technological societies among these 27 candidate planets? What could be stopping intelligent creatures from developing technology, radios, and spaceships? There are several possible answers. Earth has had major climatic disasters that nearly wiped out life completely. Perhaps a similar disaster was successful on one of these other worlds and killed it. But even with these events befalling some of our candidate planets, there should still be 25 or more potential civilizations.
So, you'd think there'd be plenty of opportunities for life to evolve somewhere else and maybe swing by the Earth, or at least call on the radio. But we haven't found any alien monoliths, or beer cans, or cigarette ends, and we have not heard them tweeting on the radio either. So, where are they? There are lots of theories about that, but I'm going to concentrate on the more plausible ones. First of all, there's the water trap. Maybe the worlds that have water on them are all ocean, for the most part. And if that's the case, you can't discover combustion, you can't make metals, so you can't make a radio or a spaceship. If our dolphin friends lived on an ocean planet, they would be stuck where they are in the Stone Age forever. Or maybe on a planet that has dry land but no metals, or very few metals. Same problem, you can't develop a technology. And how about the difficulty of interstellar travel? Maybe it's just too hard. It looks like a real challenge for us. It could be a couple of 100 years before we try that. Maybe it's just too hard. And then there's another theory, which is that we could be the first. We could be the first intelligence to evolve in this part of the galaxy. Someone has to be. We could be the elder race. So here's a time history of Earth. When you look at all the time that life has been here, nearly 4 billion years, humans have only been around for a couple of 100,000 years, civilization for about 6,000 years, depending how you count it, and our technical era only for 200 years. When you look at this picture, it is obvious that the most likely first alien life forms that we discover will not be intelligent. They will be somewhere back here, equivalent to life on Earth during the first 3 billion years of evolution. Similarly, nearby life on an exoplanet is probably plodding its way up the evolutionary ladder. Remember how long it took us to get where we are, where we could even think about life elsewhere.
We Earthlings have the prime real estate in our solar system. We may well be alone for the moment in our section of the galaxy, the only ones with space travel. If so, we need to take care of our planet and our civilization, and stick around long enough to see other intelligences and civilizations emerge over the coming millions of years on those 25 nearby planets. The American relativist John Archibald Wheeler succinctly explained Einstein's equations on relativity this way. Space-time tells matter how to move. Matter tells space-time how to curve. For theoretical scientists to move forward, Einstein's equations now need to be either proved or disproved. Two fundamental rules of the universe, as theorized by Einstein, are that light in any form moves at the same speed, meaning that space-time is smooth, and secondly, that the laws of physics are the same everywhere in the universe at any time. Since the more recent discovery that the universe is expanding at an accelerating rate, other theories counter to Einstein's have been put forward. One suggests that space-time is lumpy, and that higher energy light will feel it more as a hindrance. To put this theory to the test, scientists needed to compare the speed of two particles of high-energy light.
So you might be thinking, two tiny particles of light, why is that important? Well, you need to take the very large and the very small together to understand the universe as a whole. So far, Einstein's theory of relativity, which describes space and time as a smooth fabric that's distorted or bent by massive objects, has been a spectacularly successful explanation of gravity and the large-scale behavior of the universe. Whereas quantum mechanics, another spectacularly successful model, describes the workings of atoms, subatomic particles, and some of the fundamental forces of nature. But scientists have never been able to reconcile the two. Both relativity and quantum mechanics are equally fundamental in their own regimes. So scientists want to find a theory of everything that describes the universe as a whole.
Several ideas which attempt to reconcile relativity and quantum mechanics suggest that space and time are not actually smooth and uniform, but are instead a seething froth when seen at the smallest scale, like bubble wrap. A low-energy, long-wavelength photon is unaffected by the lumpiness of space. But a high-energy, short-wavelength photon is hindered by the froth. This makes it move more slowly than lower-energy radiation, so it breaks Einstein's law that all light particles must travel at the same speed. To test this theory, they needed Fermi, the orbiting gamma-ray detector.
We observed a gamma-ray burst. A gamma-ray burst is a huge explosion. That gamma-ray burst produced a large number of photons, one of which had enormous energy, very short wavelengths. Those photons traveled 7 billion years to reach us, and yet the highest energy, the shortest wavelength photon, arrived within 900 milliseconds of the lower energy photons. That's a little bit like racing two speedboats, one through water and the other through molasses, and having them arrive at the same time. It just doesn't happen. Because Fermi saw no delay in the arrival time of the two photons, it confirms that space and time is smooth and continuous, as Einstein had predicted. And it shuts the door on several theories of everything that had predicted that space and time might be foamy enough to interfere with light. And the observations that we've made of these two photons with Fermi takes us one step closer to achieving the goal of having a theory of everything that combines the most successful aspects of quantum mechanics and relativity into one unified theory.
Einstein's theory also predicted that gravity could bend light, an astronomical effect as seen here called an Einstein ring. Gravitational lensing is where the light of a galaxy behind another gravitational body is bent around it, forming a ring of distorted light. But do the numbers add up? And can the mass of the interfering object be measured using this theory?
So we've known for a long time that on the scale of the solar system, general relativity is either the correct theory of gravity or extremely close to correct. But we don't actually know whether general relativity is the correct description of how gravity works on the scales of individual galaxies or of the universe as a whole. So we used two phenomena. One is called gravitational lensing. So general relativity says that when you have a massive object like a galaxy, that causes space-time to be deformed. And that warping of space-time means that if you have a second galaxy behind it, the light coming from that second galaxy will be deflected. And if the deforming of space-time is enough, you can get multiple images of that background galaxy warped into what we call an Einstein ring. And the radius of that ring, how big that ring is, tells you how much warping of space-time is going on. So we used two telescopes to do this. We took an image of the gravitational lensing using the Hubble Space Telescope, and that let us measure how big the Einstein ring is. And then we used the very large telescope operated by the European Southern Observatory in Chile to measure how fast the stars are moving in the lensing galaxy. So we took spectra This is measuring how much energy is emitted basically in each color. And those spectra tell us how fast the stars are moving in the galaxy. Measuring how fast the stars are moving tells us how much gravity there must be holding those stars in their orbits. And so comparing the amount of mass that we infer from that with the amount of warping of space-time that we see from the lensing, we're able to test whether the amount of warping is consistent with general relativity.
In 1917, Einstein created the concept of a cosmological constant in his calculations to balance out gravity in his theory of general relativity. He later abandoned this concept, considering it erroneous. However, with the recent discovery of an accelerating universe, that constant might help explain dark energy.
Dark energy is a hypothetical substance that explains why the expansion of the universe is accelerating. So the universe has been expanding ever since the Big Bang, but what's odd, and we've only known this for the last 15 years or so, is that acceleration is getting faster. It's accelerating. Now, naively, you would expect that all of the gravity in the universe, all of the mass, would cause things to pull together and slow down the expansion or have it carry on going at the same rate. You can't really come up easily with a way of explaining why the expansion is getting faster and accelerating. Now, one way of explaining dark energy, one way of getting rid of dark energy entirely, is to say, well, all of that interpretation is based on assuming general relativity is the correct theory of gravity. Now, if it's not, and a lot of theoretical cosmologists have worked on this in the past, you can come up with ways of accelerating the expansion without introducing a dark energy. Now, our work, which we found that general relativity is the correct theory on the scale of individual galaxies, tells us that if you want to explain away dark energy, you have to maintain the validity of general relativity on astronomical length scales.
Another factor of Einstein's relativity is that gravity and space-time will function in a predictable manner everywhere.
The whole theories about the formation of the universe, how the universe is evolving, are based on one philosophical and fundamental assumption, which is that the laws of physics are valid everywhere in the universe and at any time in the universe. While here on Earth, we can only prove those laws of physics now and on certain circumstances. So it's very important in astronomy to also check that those laws of physics are still valid, where the gravitational fields are much stronger.
Recently, it has become possible to put that theory to the ultimate test. The effects of Einstein's general relativity will be assessed in the most extreme gravitational conditions imaginable, at the heart of our own galaxy.
We think we know that this object we have in the galactic center is a black hole, but to prove that, without any doubt, we have to come so close that we actually have to measure the fabric of space-time and see that it's that which the theory of Einstein predicts. So that's the concepts. Then comes the question of difficulty, and I have to say, ooh, that was a long path. It was very, very difficult because while gravity is sort of an obvious thing, you stand here on Earth and you sort of have an idea what it is. In reality, it's an extremely weak force, and the effects of general relativity are extremely small. So you have to measure to a precision which we are normally not used to in astronomy. Well, you see, the center of Milky Way, where we suspect there is a black hole, has stars orbiting this central black hole. And these stars are our measurement objects, if you like. They test the gravity of the object. And there's one star in particular, which we've been following now, believe it or not, for 25 years. That's more than half of my scientific career, with telescopes here at ESO in particular. And we've charted the orbit of this star, and we know then around this time, this star will make it as close as 4 times the distance of Neptune to the Sun. That's 17 light hours. So that's very, very close. And that's the unique opportunity to, in fact, test out the gravitational theory, because there gravity is the strongest. The star now moves with about 3% the speed of light, or several hundred times the speed of the Earth around the Sun. And that's when these tiny little warps in space-time, which cause general relativity to be different from Newtonian theory, to be most pronounced. So it took us about a decade between 1990 and 2000 to basically come up with robust evidence for this mass. And then in 2002, nature gave us just an absolutely miraculous star which moved so close to this object that you could see it zip around the mass in a matter of only a few years, and that gave us absolutely fantastic information. We could estimate the orbital parameters, the mass, etc., and we were fairly sure it's a massive black hole. Now the orbital period of this star is 16 years, and these measurements we took here on the then new very large telescope we took in 2002. Take 16 plus 2002, and that's 2018. So our star is coming back to its original very close position near the black hole. That's the time when we want to be there and make these measurements.
Preparations for this breakthrough observation began in early 2018 at ESO's Paranal Observatory. Their cutting-edge astronomical equipment was readied to make measurements of one of the most extreme gravitational laboratories at the center of the Milky Way.
For the discovery, a combination of 3 instruments of ESO were used: NACO, Symphony and Gravity, and all of those instruments are unique in the world. NACO is adaptive optics in the infrared. We don't have so many in other telescopes. Symphony is a high-resolution spectrograph, very important to measure at which speed the star is coming to us or going from us. And Gravity is an interferometric instrument, the only one in the world that can combine 4 big telescopes, 8 meters telescope, with a baseline of 130 meters, so having the same resolution as a 130-meter telescope. And it has, in addition, the capability to do astrometry, very accurate astrometry, so it measures movement that are the equivalent of an astronaut on the moon moving a flashlight by about 10 centimeters. And the combination of all these instruments, interferometric and classical spectroscopy, adaptive optics, is what makes ESO unique. It's having all of them on the same side in a position where you can observe the galactic center in good conditions.
So by testing, by measuring these predicted physical teeny effects, they are a very, very small fraction of what we knew so far. That's why we have to make such precise measurements. That's how we can test general relativity in this domain.
You need to get very sharp images. And the best way we can get sharp images is to make big telescopes. But since we don't have these very big telescopes, we combine telescopes. We create a super telescope, in this case, which is 130 meters in diameter.
Even with the impressive size of the very large telescope, the only way to precisely measure the path of the star around the supermassive black hole took some innovative telescope teamwork.
For our work so far, what we've done is we've taken pictures with the single big telescopes, the single 8-meter telescopes, and make them as sharp as you can be. The problem is, and you see this in my hair, there's wind. And the wind distorts the waves. And so either you go out in space, very difficult for an 8-meter telescope, or you take the 8-meter telescope and you repair the distortions which the Earth's atmosphere does, like on a hot day when you travel along a road and you see the flimmering of the distant approaching cars. So that's what we do. That's called adaptive optics, and that makes the images with single telescopes already very sharp. But that's not sharp enough for what we want to do now. We really need to make still better, still 10, 20 times sharper images to see the tiny effects of general relativity. And that we do by taking into account that ESO not only has one telescope, but 4 of these gigantic 8-meter telescopes, and we can bring them together as if it's one. That's a very challenging experiment, but we've done this now, and so we are ready to make these measurements at an unprecedented precision.
So we combine the light from 4 telescopes, the very large telescopes, here in the center of the mountain of the observatory. The 4 telescopes are separated by 130 meters, which means that our super telescope can make 20 times sharper images than a single telescope.
We have all 4 telescopes working together, and in addition to these 4 telescopes we have a beam combiner, and this combines the light from all the 4 telescopes, and this is gravity. Gravity is, of course, it's the best, because we can really trace the orbit of this star very, very carefully with really good accuracy, so we can now get very nice orbits, and we're trying to test all our theories with this very nice data we have now.
2 other state-of-the-art instruments will reveal an effect called gravitational redshift. This is visible when light from the star is stretched to longer wavelengths by the very strong black hole.
We actually expect that we can see general relativity, and how can we see that? It's actually a slight deviation of how the star is moving, and this deviation we can see in the first place with the so-called Doppler effect. It's currently approaching us, and it will fly away, and this Doppler effect is actually something we can observe by the means of spectroscopy, and spectroscopy in turn means that you need a spectrograph, and such a spectrograph is Symphony, and that is the instrument which will be the one which actually is observing the relativistic effects.
Now, after an epic 26-year observing campaign, the effects of Einstein's general relativity have been clearly seen for the first time.
So the experiment we're doing is extremely simple in some sense. We are just measuring the motion of stars around the black hole. That is very much like Earth goes around the sun, and you can actually calculate the mass of the sun from the knowledge that Earth takes a year to go around the sun, and essentially we try to do the same. We try to measure the mass of the black hole by seeing how the stars fly around it.
And right now we are observing this passage as the star moves into this critical curve around the black hole.
For scientists, a spectacular show of orbital mechanics and relativity.
So what were the most exciting moments in the observing campaign? I think actually it was in the very beginning, about 2 years ago, when we for the first time pointed to the black hole and to that star, and actually we've seen that both of them, and this was a big surprise for us, because we did not expect it. Actually, it's right at the field of view of what we have, and so this was very revealing to actually see it, that we can go to very faint, that we see the faint black hole all the time and the star nearby. And the other most exciting probably was that this year, when the star was moving so fast at a fraction of the speed of light, that you could see it from night to night. This was very exciting to see.
And the combination of all these instruments, interferometric and classical spectroscopy, adaptive optics, is what makes ESO unique. It's having all of them on the same side in a position where you can observe the galactic center in good conditions.
The beauty of it is that it's a very simple experiment in the phenomenon. Yeah, there are some technical challenges that you have to overcome to build the instrument and perform the experiment, but the concept is very simple. You can probe the black hole properties, and then you can probe the gravitational field, which is a very strong one, and up to now, whatever tests for the general relativity or this geometrical theory of gravity that we have has been in the solar system, and also some pulsars, but in this very strong regime it has not been tested. So this is just a starting point for it with the developments like instrument developments and the new telescopes. We will do more and more of this.
More than a century after he published the paper setting out the equations of general relativity, Einstein has been proven right once more with the combined resources of the ESO.
This is one of the huge benefits of ESO, and the way ESO works is that there is always a very strong collaboration between ESO and its institutes in its member states, which is very unique in the world because it enables ESO and the ESO members to undertake projects like gravity, which are so complicated that you need a strong team.
Well, what comes next? For the next years, we have a pretty good outlook of what will happen. So the next effect, which we will see, is a Schwarzschild precession. This means the orbit of the star will rotate. The ellipse will rotate a little bit. And so this is an effect which we will see next year. Pretty sure about it. Then we come to more subtle effects of general relativity, but even more exciting. This is about the space-time itself around a black hole. So the space-time around a black hole will rotate with the black hole, and so this will move the orbits of the stars yet in another direction. And this is very exciting because this property is very unique to general relativity, and we will only be able in that black hole in the center of the Milky Way, we will have the precision to measure that.
With the theory of relativity dusted off and placed back on its pedestal, what remains is for scientists to work out what dark energy is and how it affects the known universe.